Okay, welcome to our last lecture for ECE 108. So as I advertised before, this is all about some fun applications of some of the things that we've done before. You are not going to be tested on it. I just wanted to give you a real world fun takeaway that you could actually go out and get your hands dirty and testing these methods by doing some programming and doing actual stuff if you want to. Okay, so let's end the term with some fun applications. In particular, we're going to talk about Monte Carlo methods. So a Monte Carlo method, very rough definition, is a method that uses random samples to compute something numerically. Very vague because these methods can be applied to a ton of things. So generally the convergence is slow. By this, I mean you generally need to use a lot of random samples to get good convergence. If anyone is interested in like the convergence of algorithms, that type thing, the convergence is actually the square root of n, where n is the sample size that you use. So if you want to decrease your error by, say, a factor of 10, you have to increase your sample size by a factor of 100. So that's horrid, but these are good methods for really hard problems. And in some cases, they can converge sufficiently fast. But these are often easy to implement, and basically all of science where you collect data is a kind of Monte Carlo method. So as I collect my data, I'm collecting random samples, right? And then I'm using my random samples to try to come to some conclusion, and I'm basically taking my random samples and doing something numerically with it to try to compute whether or not my hypothesis is true. So yeah, science is a Monte Carlo type method, and if you ever see a scientific paper with really small sample size, that's bad because, again, the convergence is generally slow. Okay, so just some hot topic real world applications include integrating. So if I give you a function, tell you to integrate it, you can use a Monte Carlo method to do that. Fluid dynamics, climate change forecasting. So there are a lot of unknown variables in climate change forecasting. Like, what is the power output of the sun going to be over this wide range of parameters? What are the various coefficients for different things, like quantifying, say, turbulence at the small scales or even at geostrophic scales? All of these type things are fuzzy data. You don't really know exactly what they are. So that randomness allows you to use Monte Carlo methods to help get a better model for climate forecasting. Other examples, computer graphics. Say if I want to model some particles going around, like a bullet hits the ground and dirt kicks up. Well, Monte Carlo simulations can be a good method of doing that, and ray tracing can be another one. So I have light that shines on something and it scatters. So as my light comes in here, and say scatters in different directions, I can use Monte Carlo simulations to get a good approximation for where this various light is going to save myself some time in doing all of this ray tracing. So enough with talking in vague, this is what it does. Let's get our hands dirty. Monte Carlo methods calculating pi. Use expected values or probabilities to calculate pi. So how can we do this? Well, I'm going to do all of this on Mr. Paint. Okay, so I have a circle. I want to use this somehow to compute pi. Well, I want to know a geometric property of this circle to be able to use pi. So previously, if I go over here, I said that these methods can help me do things like integrating. So that's really what I want to use here. Okay, so a natural question I can ask is, what is the area of this circle? Well, I have fair game in picking what the radius of this circle is, right? I just want to compute pi. I have no limitations on this circle. I just drew it. So here I could say, let's just for simplicity say that this circle has a radius equal to 1. Okay, so if the radius of this circle is equal to 1, what is the area? Well, area is pi r squared, right? So the area of this thing here, so just A, is simply going to be equal to pi. Okay, how does that help me? I know the area of this thing is pi, and somehow with Monte Carlo simulations, I need to use random variables and random samples in particular to do something, right? So how can I use randomness to do this? Well, it turns out that the natural way of going from here is I can put a square around this. So I know what the area of this square is, right? So since the radius here was 2, the length on each of these sides is 2 here. So the area of this whole thing, including the area of the circle, is simply going to be equal to 4. Okay, now I kind of have some options on how I want to try to build a random experiment that might be able to calculate pi. Well, so a natural first place to start is asking, how can I introduce randomness? Well, I can do that by picking a random point uniformly from the inside of this box. So if I pick a point here, or any of these points, just pick a random point. That could handle my random sampling. And now I need to somehow tie those random points to this area inside the circle versus the area out here. Well, there's 2 ways I can do this. I can look at probability or expected value. So first, let's look at probability. So if I pick a random point, I can ask, what is the probability that it's inside the circle versus the probability that it's outside of the circle but still inside the square? Well, if everything's uniformly distributed, then the probability of being inside the circle, given that I'm inside the square, will simply be pi, the area of the circle, divided by 4, the area of the square, will be equal to the probability that my point, whatever my point is say inside the circle. So I'll just do a big circle for the circle there. Okay, so again, why does this work? Well, if everything is uniformly distributed and I'm picking random points, then the probability that I'm inside this circle is the sum of the probabilities that my point was any of the values inside the circle. This is a continuous problem. So for continuous problems, I have to integrate. I kind of hinted at that before, but that's why I get a pi for the probability that I'm inside here, and the total possible outcomes of where I could be, well, that's 4, because I'm picking a random point inside this square, and the square has area 4. So this is one way to tackle this. So let's undo those bits there. I also said that you can tackle this via expected values. So let me clean this up and look at it from expected value. Okay, so to introduce expected values, I need to have a random variable. Well, what's a nice random variable to use? Well, here, let's just say x is going to be a random variable that is 1 in the case where my point is inside the circle, and it's going to be 0 otherwise. So 0 when the point is not inside the circle. So this would be my indicator random variable. So here I want to compute what is the expected value of x. Well, since this is an indicator random variable, the expected value of x is going to be exactly equal to the probability that x is equal to 1. That theorem 40, I believe. So from here, the probability that x is equal to 1, well, this is the same thing as the probability that p is in the circle. So again, using expected values, I get the exact same result that I had over here. So it doesn't matter which approach I use, I end up getting the same result. Okay, so let's go to practice and actually build an algorithm that does this, well, show you an algorithm that does this, and run it for a couple cases. Okay, so let's make this big, and let's jump over to here. Okay, so this is kind of overly zealous way of doing it, so I can turn on the plotting pretty quickly. So here, n is going to be my sample size of the number of experiments I want to do. Inside, this is going to be a metric for if I'm inside this circle. This stuff you can ignore. That's just to quickly turn on and off the plotting for these demonstrations. So what do I want to do? For each one of these values of ins, I want to generate a point inside this region. Well, statistically, it doesn't matter if I do this whole square or if instead of doing the whole square, I simplify the problem a bit by instead only considering one quadrant. I get the same result, right? Since I have symmetry across these vertical lines here and here, right? It doesn't matter if I do the whole thing or if I just focus in on this little quadrant, say here. So that's what I'm actually doing here. It doesn't really change the runtime or anything like that. It's just a bit more convenient with the way that random numbers work. So here I'm picking random points, and just by using this function here, I'm picking 2 points, and so here by using this function here, I'm picking 2 random numbers that will be between 0 and 1. So here notice that this radius is 1, so if I call this point here 0, this point up here is 1, and that point up there is 1. So I'm indeed, by using this, in this little region here. I could have done the whole thing, it's just Rand default does it, so why not do it this way? Okay, so now what I want to do is I want to compute whether or not that point that I picked is inside this region here or outside of that region. Well, what do I know about this? Well, I know the radius here, if I'm going to be inside of this, then it needs to be the case that the square root of x squared plus y squared, this will be the distance from the origin to whatever my point is. So say if my point's there, this thing here, I need this to be less than or equal to 1. It doesn't matter if I do less than or equal to or strictly less than. Either or gets me the same answer because the probability of being exactly 1 is 0. But from there, that's what this statement here says. If the norm of point comma 2, so if the L2 norm, this quantity, is less than or equal to 1, that point is on the inside, and if I have my plotting on, it'll plot it as a blue point. Otherwise, it'll plot it as a red point if I have plotting on. And then from here, to compute pi, well, if I go back here, pi divided by 4 is equal to this probability. So pi itself, just from all of this, pi itself will simply be equal to this probability, or in my case, inside divided by n, that the point that I picked is inside the circle, and all of this would then be multiplied by 4. Let's go over to here and run some samples. Okay, so for 10 to the third, I can run this pretty quickly and show you the points. So let's see what this looks like. So if I run this for 10 to the third, this is what my picture looks like. So again, it plots it blue if it's inside my circle, and it plots it red if it's outside my circle. So I said that my numbers were between 0 and 1, so I'd only deal with one quadrant. So indeed, I am only dealing with one quadrant. And here it's saying that pi is approximately 3.19. Well, it's 3.14, so this really isn't a good approximation. I can run this again. So with the way that I have this set up, it will generate a new figure. So for my new figure, I get something that looks basically identical to the original one. So let's just delete it. And this time I got a slightly better approximation of pi. So just to show you how this fills out a bit, if I run this 10 to the fourth, this should run fine. It might take a little bit, so yeah. But running this, I'll get a better approximation. And here, I'm running 10 times the number of points, so it's going to be much more well-resolved. So again, much more well-resolved here, and I get 3.16. So again, not the best approximation for pi, but I did say these methods are slow. And here you can see I'm starting to fill in this little area here. So let's turn off this plotting. So false. And let's crank this up. Yeah, let's do 7. So here I get 3.1407. So we know pi is this value, right? So we are off by a fair bit, but it's not the worst. So let's compute the relative error. I'm off by 0.02%. So it's not the worst for some applications, but yeah, slow methods, but this is how Monte Carlo simulations work. So let's save this and then look at the next application. So what about evaluating integrals? So use expected values to approximate this integral here. Okay, so let me just copy this over so I have it. So how do I do this? Okay, so how do I do this? Let's ask Mr. Paint. So let's just copy this over and here we go. So in this case, I want to evaluate this integral, right? So I know how to do that analytically. So you know how to do it. It's a basic integral. So the integral from 0 to 1 of x squared dx, this is simply going to be equal to 1/3. So how could I use a Monte Carlo method to do this? Well, let's plot this thing out. So x squared looks something like this, right? Let me make it look a little bit better. So x squared looks something like that. There we go. And I want to integrate this from, say, 0 up to, say, call this point over here 1. Okay, so in doing this, I really want to find the area under this curve, just from the definition of the integral, from here all the way over to here. So I want to compute this, say, blue area. So since I want to use a Monte Carlo method, why don't I do something very similar to what I did for pi? Basically identically similar. So I'm going to compute whatever this maximum value is here, and I'm going to build a little square, and my plot wasn't square, so it's not perfectly square. And here, just to fill it in, to make it look a little bit cleaner, I'm going to fill that area in there. But you know this should be all squared up and all that good stuff. So here, what I can then do is I can pick random points somewhere in here, things like this, and I can ask, what is the probability that these points are underneath this curve? If I do that, I will approximate this area. So just to be a bit more formal before I show the algorithm for doing this, I know in this case, when x is equal to 1, this thing is equal to 1. So I'm again dealing with this square going from 0 to 1 in both the x and the y direction. And from here, I want my points, my inclusion criteria will be that for whatever random value that I picked for x, so I'll call that x sub I will want it, when I square it, to be less than or equal to y sub I, where y sub I is the point that I pick for y. And again, these x sub I, y sub I are going to be random. So from here, I would want to compute what's the probability that x is, say, in the blue area, which I'm just going to denote by this thing symbolically. So this is the probability we want to compute, and I'm going to do it via this inclusion criteria. So let's go over to MATLAB and see how that works. So integrating x squared. So in this case, this is very similar to the code that I had before, and this thing here is saying I want my y minus my x value quantity squared to be less than or equal to 0. And if I go over here and subtract off the y, that's exactly what I have. I just always got used to using this form of the criteria, so I'm going to use it here. So again, everything else is the same here. I pick 2 random points and fill it out. So the plotting is on. I'm going to show you the little thing. So let's see what this looks like. Okay, so this is what my first result looked like. Remember, blue means I'm included. So if I compare this picture to this picture over here, you can clearly see that I have similar behavior. It is doing what I want it to do. Let's see how good our approximation was. It should be 0.3 repeating. That was 0.308. That's not the best, so let's just crank this up again. So 3 to the 6, and we'll just say that's 0. Now let's rerun this whole code. And from here, 0.3331, that's not too bad. If I add a factor of 10 here, this should improve my accuracy by a factor of the square root of 10. So basically by a factor of 3. So I might get this last digit on average. I don't know. Let's find out. So if I run this, I'll wait. There we go. I got an extra digit for that case, but that doesn't mean anything. I need to test multiple cases to see what this looks like. So here I didn't quite get the 3, so it wasn't quite enough to get that. You can quantify the error of Monte Carlo methods, but it does need the standard deviation, and that's something we're not going to cover. Okay, so that's another example of using Monte Carlo methods. But so far, like the method of computing pi might have been novel, but this isn't anything that's super duper special or anything like that. So let's look at another example and see how we can apply this to, say, double integrals. Okay, so here's your little notes from that work. So here, let's use expected values or probabilities to approximate this double integral. So here, to draw this out, I'd really need to visualize everything in 2D. I'm not actually going to do that in full glory. It's just a plane. You should know how to plot that from Math 119. But let's talk about the analytics of this question a little bit. Can I exactly evaluate this integral? Well, the answer to that is yes. Of course, it's straightforward. I can integrate with respect to x and y. That will give me a 1/4, and then when I plug in the values, I'm simply going to get 1/4 coming out. Okay, so how would I apply a Monte Carlo method to this? Well, I said before that Monte Carlo methods are really easy to implement. So let's just kind of think of what I did previously and try to apply that here. So to do a Monte Carlo method, I'm going to need 3 random variables. I'm going to need to know what x sub I is. I'm going to need to know what y sub I is. And I'm going to need to know what z sub I is. Right? So from here, I have this curve. So here I have my xy is equal to z is the curve that I want to be under. So I'm going to need it to be the case that xi times yi is going to be less than or equal to zi to be underneath this curve. So here, this bit here is just coming from my integrand. Okay, so from here, this term here is going to be my inclusion criteria. The next thing I need to work out is what is the domain size I need to work with, and do I need to divide by anything in this case? Well, if I just draw a real quick and dirty version of this, the largest that x times y can be equal to is going to be up here at 1. The largest that x can be equal to is going to be at 1, and the largest that y can be is going to be at 1. So here I actually have this cube, so my horrible 3D drawing, but here the cube is going to be my sample space, and the area of the cube, so area, is simply going to be equal to 1 in this case, right? So since that area is equal to 1, I don't need to divide by anything. So here I'm just going to strictly pick numbers between 0 and 1 for x, y, and z and see if they fit this category. Okay, so let's go to the function for that. So this is integrating in both x and y. So the only real difference is here I'm now picking 3 random variables. Here I want z minus the product of 0.1 and 0.2 to be less than or equal to 0. So then from here, if I want to do the plotting, I would plot this, and then I'd plot my triple thing. So let's just do the quick and dirty version to see what this looks like. And I got 0.27. So here's the plot with everything corrected. So in this plot, what do I have? Well, I'm just looking at a top-down view. That doesn't tell me much, so let's move this. So here, again, these points are indeed the points that are underneath this curve. The red points are outside of there. And the average of the number of points that are in here is 0.27. So it's giving me an approximation of the area. So again, I can run this with, say, more values. Don't want to go too extreme, but if I run that with 10 to the 4th, let's see what I get. Okay, so from here, I get a lot more points, 10 times the number of points that I had before. And if I pull this away, you see that here I get this area under the curve here. That's where my little blue dots are, and I get a better approximation of 0.247. So I will save this plot as the plot post. And one thing to note that you do see some of these red dots poking through. That's only because the dots have a finite fixed size, and that size can interfere with the curve here to cut through it. So yeah, Monte Carlo methods work in this case. One thing to notice is that I could have evaluated this integral analytically as well, right? So where these methods really shine are in the cases where I can't analytically evaluate something. So let's look at a case where I can't analytically evaluate it. So again, there's your little visualization of what we did in the video. Use expected value or probability to approximate this integral. So the issue with this integral is you can't compute this integral analytically on this domain. You can on the full domain, you just can't do it on the partial domain. So in order to solve this, I need to use numerical methods somewhere. So since I'm using Monte Carlo methods, it's nice to know what the exact value of this integral is, so I can compare how well the method worked. So just popping over here, we can compute this real quick. So this will be the integral of e of x squared times y squared for x from 0 to 1 for y from 0 to 1. So analytically, we can't compute this here. See, if I hit equals, it simplifies it to this, and yeah, you can't do anything else. But from here, I can say this is approximately equal to 1.135. So from here, this I can say is approximately going to be equal to 1.135. And let's just double check. Perfect. Okay, so we're expecting to get an answer around here. So if I want to use Monte Carlo methods, I'm going to do the exact same thing that I was doing before. So let's just examine what my domain would look like. Well, here I have kind of a problem that I didn't have before. So in the x and y direction, I'm again going to have that it's over here at 1 and 1, right? But this e to the x squared, e to the y squared monotonically grows as x and y get larger. So the maximum over my domain, so over 0, 1 squared of my e to the x squared, y squared is going to be equal to e. E is not equal to 1, so up here I'm over at e. So if I were to compute the volume of this new cube, so explicitly the cube that I'm working with is this cube, something like this, the area of this cube is now going to be equal to e. So now when I go to compute my probabilities, I have something similar to what I had over in this case. So here, the answer that I want isn't going to be straight given to me. I have that dividing by the e to deal with. So in particular, if I write this out, my expected value of, say, the points that are going to be underneath my curve, so I'll say points that are under my curve, this thing here will be equal to the area that I want to find, so explicitly this double integral, divided by the area that I was picking points in, and the area that I'm picking points in this case, is now e. So if I want to actually compute the area, I need to take the expected value that I find and multiply it by e. So explicitly. Okay, so in the other cases, this wasn't a problem because the areas were always equal to 1, because the area of my sampling area was always equal to 1, but now I have to do this normalizing by e. Okay, so if I go through and find the metric for points that are under my curve, what would that be? Well, following the previous method that I had before, I want my xi and y sub I to satisfy the property that e to the xi squared times e, this thing is going to be less than or equal to my z sub I. That will guarantee that I'm below that curve where z is equal to this thing here. Okay, so let's look at this in practice. So here I do the exact same thing as I did in the previous code. I also had that same error, so plot 1, so I do plotting. So here, the only difference is now point 3 isn't in the same domain as my first 2 points, right? So in order to stretch my domain in that direction, I'm just going to scale it by exp of 1. So from here, that's just scaling it so that my third point does have the correct domain. And this is just doing my check. And here again, I'm picking a handful of points and plotting it and approximating the integral. So again, I expect this to be around 1.135. Let's see what we get. So running 10 to the third points, I get 1.17. So off by a fair bit, depending on how accurate you want it. And if I look at my plot, this is what I get. So I have this whole little area under here to play with, where this kind of approaches 1, and my points are all kind of nicely in there. I have these points up above it. You do note that this doesn't actually go to 3 if I kind of get the angle right. Yeah, anyways, this doesn't quite go to 3. So there you have it. That looked rather sparse, right? So let's just bump that up in order of magnitude and just kind of fill this out because we have a bigger sample space than the other questions. Okay, so just looking at this, I have 1.15, which is a bit better than I had before, but not ideal. And now that I'm plotting a ton of points, it's not going to like rendering it. But here you can see I have lots of points that are under the curve, lots of points that are over the curve. And if I wanted to improve the accuracy of this method by using the same number of points, what I could do is, say, cut out a plane over here. Actually, let's do this in Paint. Okay, so now that I move that around. So here, the kind of inefficiency of this method is that I have a bunch of points out here. So say if I could take a plane or something like some plane like here where I cut out all of the points above it, I can improve the convergence of my method since I have less red points that aren't really contributing to helping me. Okay, so now let's go back to our lecture slides and finish things up. So yeah, so here to compute this one, I get this little sample space here. So this is Monte Carlo methods in a nutshell. If you can ever turn a problem that you want to solve into a problem of computing an expected value, you can compute approximations to that expected value by generating a bunch of random samples. Okay, so assigned reading, we actually do not have that assigned reading. I did not change the slide, so ignore that. But we do have a meme. So brute force, Monte Carlo simulation, calculating pi. So generally speaking, you do not want to use Monte Carlo simulation to calculate pi. It is an atrocious method to do it. It, again, converges like the square root of n, where n is the number of iterates of the algorithm that you do, whereas brute force, there's methods that converge like n to the fourth. So there's methods for computing pi where you can get like 4 million decimal places by doing something like 9 iterates. So yeah, I kind of can't believe this is the last lecture already. I hope you very much enjoyed the term. If you have not yet, fill out the survey. And if you have any questions on anything leading up to the final, feel free to ask in Piazza or on office hours. So yeah, it's been a real pleasure teaching you, and I wish you the best in all of your future academic careers and everything else in your life. So to leave you with a fun meme, when the professor teaches you Monte Carlo simulations right at the end of the course, but only teaches you barely enough to apply it for a handful of cases.